Now we come to question number 13. Two heavy plates are joined together at 90 degrees to each other. A laminar sheet of mass 30 kg is hinged at the line AB joining the two heavy metallic sheets. The hinges are frictionless. The moment of inertia of the laminar sheet about an axis parallel to AB and passing through its center of mass is 1.2 kg meter square. Two rubber obstacles P and Q are fixed, one on each metallic plate at a distance 0.5 meters from the line AB. This distance is chosen so that the reaction due to the hinges on the laminar sheet is zero during the impact. Initially, the laminar sheet hits one of the obstacles with an angular velocity of 1 radian per second and turns back. If the impulse on the sheet due to each obstacle is 6 Newton second, A. Find the location of the center of mass of the laminar sheet from AB. B. At what angular velocity does the laminar sheet come back after the first impact? C. After how many impacts does the laminar sheet come to rest? So here is the figure given to us, and we've been given the data in the question and need to solve it. The figure looks quite difficult to comprehend, right? But let's see, it looks like a very lengthy and a very difficult question. Let's see how we crack it.
So in this question, if we see a point of impact, let's say when the sheet is coming towards the P part and it's colliding with it, we can look at that problem as a normal linear collision, we can say basically. So if we take the initial velocity to be VI and the final velocity after the collision to be VF. Now if we see from the side angle, suppose this is one of the plates, this is the P thing which is to which the plate is colliding, and from here the plate is coming, the center plate which is attached. Let's say it is coming with some velocity VI and it is going after the collision with some VF. Here you will see that I've taken the directions as we need them so that in the final situation we'll get all the positive values. I'm leaving no scope for a negative value over here. Now if we take VI and VF, we get that delta V should be equal to VF plus VI, right?
Right.
Because they are in the opposite directions, the magnitudes get added, and as I said, all of them are positive values here. The directions we'll take care of them by ourselves and not by the signs.
Right.
Right. So delta P will be given to us by M into delta V, which will be equal to M into VF plus VI. Right. Now we know that VI will be equal to R into omega, where we can say R is the distance of the center of mass from the hinged point. If we take the top view, suppose over here these two plates, this is P over here, this is Q, and this is our plate, it is coming here with omega. You can again see that the direction of omega is taken to be the one which we need, and so again we'll have to get positive values for all of them. And if we get this is the center of mass, we see that this distance will be equal to R, right? So VI will be equal to R into omega. Now the initial condition says that omega is 1 radians per second, so VI will be equal to R into 1, which will be equal to R, and letting the final angular velocity, let's say this is Wi, the final angular velocity omega f we'll get, if we let that to be omega f, we get that Vf equal to R into omega f, right? Now we know that delta P is equal to 6, right?
Right.
So we get 6 equal to 30 into R plus R omega, from which we get that 1 by 5 into omega plus 1 into R is wait. I'm sorry. Here we will get that 1 by 5 is equal to R into 1 plus omega, right? After we solve this, basically. Now here what we see is we have got just one equation and two variables. So what can be done over here is, since we have conserved only the linear momentum right now, we can conserve also the angular momentum at the time of collision, right? So we'll conserve the angular momentum about the hinged point from the diagram, which we can see here I'm marking as O, right? So about the marked point, the change in the angular momentum, which is delta L due to the collision, will be equal to I, which is the moment of inertia of the plate which is rotating, into omega I plus omega F. Here I am using the plus sign because I have taken the omegas to be in the opposite directions, and so that negative sign for the delta is taken care of over here, right? So from this we will see that delta L will be equal to delta P into 0.5, right, equal to I into 1 plus omega. And so delta P is 6. We get that 3 equal to I into 1 plus omega, and this I will be the moment of inertia for this body, this plate. Basically we'll get the moment of inertia passing through center of mass is given in the question, but we need the moment of inertia for an axis passing through point O. Right. So what we'll do is we'll use the parallel axis theorem here.
Yeah, right.
Simple. So the I will be given to us by I center of mass plus m r square, which will be equal to 1 plus 2 plus 1.2 plus 30 into r square. This will be, and this we'll put over here in this part, and 1 plus omega we had found out is equal to 1 by 5 r in the equation over here, right? So putting in both of these values, we'll see that we get two values of r. It basically turns into a quadratic, and two values of r are received, which are 0.4 meter and 0.1 meter. However, the center of mass can't be at 2 points, right? So we need to find the right value. Now if we plug in the value of r as 0.4 into this equation, we get omega equal to minus 0.5, right? Now we can't get omega as minus 0.5 since all of the omegas which we assumed were in the correct direction, as I mentioned earlier. So this negative value is not a possibility. So r has to be equal to 0.1. Plugging in r equal to 0.1 into the equation, we get omega equal to 1 radians per second. This is a positive value as we needed, and so we can be sure that the r value of 0.1 meter is the one which we needed. So here we see that the body is coming back with an omega of 1 radians per second, which was the initial omega also. So here we see that the initial and final omega are same. So what we can see over here is, now again the part will go and collide to point Q, again with the same impulse it will come back with the same angular velocity, and so there will be no dampening happening anywhere, and thus this oscillation will keep going forever and it will never come to a stop.
Okay, right. So in this question we basically saw the concepts of rotational motion in detail, right?
Right.
And it was a lengthy question, but how important are such questions from JEE point of view?
It's very important because here what we saw was that in an initial situation, people would have tried to solve it only with the linear equations. However, you see, without the rotational angular equilibrium equation, we couldn't have gone ahead because we had got just one equation and two variables.
Right.
So the rotational motion helped us get a second equation, solve the two equations, and get the value of the r, which is the distance of center of mass from the hinged point. And also we found out that the omega is same after the collision, which gives us that the process will keep going on forever.
Right. Okay. So that was question number 13. Let's move on to question number 14 now. A cubical block of side L rests on a rough horizontal surface with coefficient of friction mu. A horizontal force F is applied on the block as shown. If the coefficient of friction is sufficiently high so that the block does not slide before toppling, the minimum force required to topple the block is A. Infinitesimal, which is very small, B. mg by 4, C. mg by 2, or D. mg into 1 minus mu.
Okay, so in this question, we might feel at the first look that even a slightest push of force, that is an infinitesimal force, will help the block to move up. What we need to find out over here is what is the minimum force which will make this block topple about this point, right? So now here what we'll see is actually an infinitesimal force won't work because there is another force, that is the gravitational force acting at the center of mass over here, which will negate the effect of this force.
Right. The torque of gravitation will be opposite in direction to the torque of the force F.
Right. Because the toppling is happening about this point, the torque due to the gravitational force makes the body rotate in this direction somehow. You can see that the force is over here, so it will make the body rotate in this direction. However, this force, since you are pushing it over here, it will make the body rotate in this direction. You can see that these two are opposite motions. So what force we need over here is the one which can negate the effect of this gravitational force over here, and as soon as this is negated, the block will start to topple. Right. So what we need to...
But we don't want it to slide, right?
No.
So it should be less than the maximum frictional force.
Yeah. We don't need to worry about that because the question says that if the coefficient of friction is sufficiently high. So the question solves that problem for us. It's a very simple problem now. All that we need to do is find the torque which will help us overcome the torque applied by this gravitational force. So writing the torque equation about this point O, we get the torque about point O will be, assuming the anti-clockwise direction to be negative torque.
Okay.
We get the torque due to the gravitational force as mg into L by 2, because the line of action of this gravitational force is at a distance of L by 2 from point O.
Right.
But since this is in the anti-clockwise direction, it will be a negative torque.
Okay.
Right? This plus the torque due to the force will be, as you can see, the distance of application of this force is L from the point. We get F into L.
Right.
Right? So this is the total torque about point O, and this block will start to topple as soon as this torque becomes positive.
Right.
Right?
Right.
So we need this quantity to just become positive, so we equate it to 0.
Yeah, to find out the limiting value.
Right. And as soon as the F goes infinitesimally above that value, the block will start to topple. So we equate this to 0. From here we get that F into L should be equal to mg L by 2, and cancelling these two we get F is equal to mg by 2. Simple as that.
Okay. So this was a fairly easy question. We just need to understand understand the concepts of torque and force, basically.
Here what we need to understand is the point about which the box will topple. Generally we take the moment of inertia and everything about the center of mass.
Right.
However, here we could see in the question that the block is going to topple about point O under this situation.
So yeah, if someone by mistake considers the rotation about toppling about center of mass, then they might answer infinitesimal, because then
Possibly.
Yeah. And here another thing is that whatever frictional force is present will have no impact on the torque, because the line of action will pass through the point O. Right. So this was question number 14. Moving on to question number 15. A ball moves over a fixed track as shown in the figure. From A to B, the ball rolls without slipping if the surface BC is frictionless and Ka, Kb and Kc are the kinetic energies of the ball at A, B and C respectively. Then 4 options are given to us regarding the heights of A, B and C, A and C and their comparison, and regarding the kinetic energies and their comparisons. Let's see which of the options is valid.
Okay, so here what we can see is that the work done by friction while the body goes from point A to point C. Let's write down this as point A and point C. While the body goes from point A to point B, the friction is there which causes the body to start to rotate. However, we see that the work done by friction on the body will be 0 because there is rolling condition, and in that situation the point of contact is at rest, and so the work done by friction is 0. So, and for the part B to C, there is no friction, so there is no external force, no work done. All the work done is only by the gravitational force, and that can be considered as the potential energy. Now moving on to analyze this problem, when this ball starts from point A and comes to point B, it will start to rotate with some velocity omega, angular velocity omega, and have a linear velocity v, which will be equal to r omega. And when it goes from B to C, since there is no friction force involved, the angular momentum will not change as there is no torque, and omega value will remain constant. However, as it rises up, it will lose its translational kinetic energy which exists because of the V, and this will get converted into the potential energy. So the situation can be visualized over here as the ball starting to come down from part A to part B in a rolling situation. Here it comes down, rolling, and when it goes to B to C, it keeps rolling with the same speed. Here the rolling speed increases, here it remains the same since there is no external torque. Right? So what we can see is at point B, all of the potential energy is converted at point B. All of the potential energy is converted to translational kinetic energy plus rotational kinetic energy. Right? Now, when it goes to point C, the rotational kinetic energy stays as it is. However, this translational kinetic energy is converted to potential energy. So, now the energy at point A, total potential energy at point A, which was converted to the kinetic energy at point B. I'm sorry about this mistake, it is the kinetic energy over here. All the potential energy at A has been converted to kinetic energy at B, split into translational and rotational. However, at point C, the rotational kinetic energy stays as it is, whereas only the translational part is converted to potential energy. So this shows that the potential energy at point C is lesser than the potential energy at point A, which can easily get us to the conclusion that HC will be lesser than HA. Do you get my point? So HC lesser than HA is the option only available in option A and option B. So we need to go ahead and analyze the kinetic energies at point A, B and C. Right? So the kinetic energy at point A is 0 as we know in the beginning. Right? At point B, it's the total energy as the kinetic energy. So we can easily...
potential energy is 0.
Right. So we can easily assume that the kinetic energy will be maximum at point B. Right? Among the entire situation. And at point C, there will be some kinetic energy which is only the rotational part, because the rotational part doesn't change from B to C. In option A, we see that KB is greater than KC, which is exactly the situation because at B it is maximum. At C, there is only a part of that which exists.
Right.
But and
as in, why don't we check after option B also? If it's a multiple choice question, suppose, then we need to compare KC and KA also, right?
Right. So now KA, we know that at point A, KA is 0. Right?
Okay.
Because it's not moving at all. That's just the beginning point. Whereas at KC, we have the rotational kinetic energy available with us. So in any case, KC will always be greater than KA, however less the speed of rotation is. Right? That brings us to the conclusion that point A is the required answer over here.
Okay. Why point B can also be the right answer?
B can't be the right answer because it says that KC... Okay, wait. KC is greater than KA. Okay, so this can be a multiple choice question and KC is also probably right because KC is greater than KA. That's my mistake on my part. KC is greater than KA, so point A and B
it's a
multiple
multiple choice question. Right. So the answers are A and B, and that was question number 15.